explanations over here. Okay. Okay. Why we want to have this kind of definitions here? Okay. Okay. So just give you remarks here. First of all, this sigma x must be a subclass of sigma x must be subclass of discrete f. Okay, so that means we have a fewer subsets over here. So why we want to study this sigma x? So the reason is here. So because when we look at one random variable x, okay, so that means we are only interested on certain cases, okay, maybe situation or cases only. Okay, for example, so let's say we only know a number of, for example, we interested of number of head in 5 poses. Okay, we interested on number of head in 5 poses, but okay, so for example, let's say we look at the number of head in 5 poses is 2. Okay, so this is good enough already. So we happy. Okay, so we don't bother whether, so we don't correct. We are not, I mean, any interest in this case. We are not interested on which toes give head. So it could be the first toes and the third one, or it could be the first and the fourth, or it could be the third and the fourth, but we don't care as long as there are 2 occur in the 5 doses. We're happy already. Okay, so that's why with this x we only interested on certain situations. Okay, only certain cases for it. Okay, so since we only interested on some special case only, certain situations only, so then with this sigma x, okay, it's already enough for this, for us to analyze those cases. So that's why we don't have to look at the bigger sigma field. We just look at a smaller one. We have fewer event that we know we need to look at it. However, that is already enough for us to analyze the data. So that's the reason why we look at this sigma field generated by a random variable here. Okay. Okay. I think later on we're going to look at it. Okay. So in this case, let's look at the examples here. All right, so let's look at the very simple one. So x is an indicator, random variable. So 1a. Okay, so then we can see we only have 4 chances only. So empty set A, C, A, or omega. So it depends on whether 0 belongs to this B or not. Okay. So I think you can verify it easily. So the pre-image for X inverse B will be like this. So in this case, the sigma field generated by X will be empty set AC, A, and omega. So we can see with this 4 event, so it's already enough for us to analyze this case. Okay. So this is what I mentioned just now. Okay. So if omega is cuttable, P omega is usually chosen as the sigma field. So, and note that omega x is only 4 elements inside. So this will be much smaller than this P omega. So this is the main reason why we consider a random variable and this sigma field generated by this. Okay. So the reason is we can look at a smaller sigma field, but it's already enough for us to analyze the data. Okay, so that is the idea for it. Okay, so that's it for this chapter 2. Right. Good. We have 1 hour. Okay, let's carry on. We continue to tutorial 1. Yeah. Okay, so I think maybe before we start our tutorial, so I give you guys a short break for about 5 minutes. Yeah. Then we carry on to our tutorial.
Can I ask a question?
Yeah, sure. So the rest can answer the rest.
So I just want to clarify again. When you define the random variable, you say it's a function. It takes the sample space into rails, and then you take the inverse, right? You can take the inverse of the Borel sigma field of rails to bring it back into our sigma field. So I mean, so if x r, why isn't the inverse just r to sample space? Why? Yeah.
So sorry, I'm not sure.
Because it's kind of like a circle.
Sorry, can you repeat again? I'm not sure whether it's my connection problem or yours. I can't hear you clearly. Just repeat your question once again.
Okay. So you mentioned that x takes the sample space to rails.
Okay.
And x inverse takes the Borel sigma field of rails back to the sigma field, right? So why doesn't x inverse just take rails back to the sample space?
Okay. This is actually in an issue of mathematics. You guys, I think, probably know this, right? We have things so-called one function, on two function, one to many to one, things like that, right?
Yep.
So the reason is here. Let's say if you have a function, maybe okay, let's say omega to r. Okay, let's say you have a functions. Okay, I don't want to put a symbol there. You have a function from omega to r, right? So first thing, I think this is I think you guys have learned in calculus, right? So first of all, the inverse for that particular function might not be a function. Am I right? I think you agree with this, right?
You may not. The inverse may not exist, lah.
So yeah, the inverse might not. I mean, not exist mean it's not a function. Am I right?
Okay.
You get an example. So for example, if you are taking f of x to be x squared, okay, and if you are taking x to be everything in r, yeah, so you could not find an inverse function for it. Okay. To be more precise, okay. To be more precise, this might not be a function from r back to omega. That's the thing, huh? We have to be very specific here. So for example, like I said, if you're taking fx to be x squared, x to be r, that is the case over there. So that's the reason. So that's answer your first question. You are asking me, if you take You are asking me if you are taking x is a function from omega to r, why not we are taking the inverse from r back to omega, right?
Yeah.
That is the first thing that the first answer for your first question. So that's the reason. So that's why alternately what we can do is we use set instead of we use subset instead of a number. So that's the thing. If you have a function from here to here, then the inverse is always bring every subset here back to another subset here. Okay, it's always bring any subset here back to any subset here. So there's no issue. So that's the reason why we are looking at inverse for the set instead of the inverse for the particular numbers. Okay, so because you have an issue, you cannot bring a number back to this because of which is, but you can bring to here. Okay, so this is the general mathematically we have this thing. Okay, now this is in general if you function like that, so it bring this back to here. So yeah.
Sorry, yeah, can I interject? Yeah, so then, but this is the thing that that's sigma field, right? That P is that sigma field?
No, this is a power set. Power set.
Oh, power set.
Power set might not be a sigma field, right? So that's why.
Yeah.
That's the thing. In general, although I'm saying that almost all the functions are random variables. Yeah, actually, if you ask me to give you one example of non-random variable, I'm sorry, I couldn't name it. I also can't name it. A very obvious one. Okay. So in general, a function, the inverse function map any subset here back to a subset. I think we all know this. Okay. A random variable is a very special kind of things. So a random variable is a function is you will map a Borel subset here. Okay. The inverse for random variable will back to a event here. So if a function meet this criteria, we just simply call it a random variable. Okay.
So in this case, can F be a Borel sigma field of the sample space?
Which one? This one.
Yeah, number 2, that F.
Yeah, it depends on what is your capital omega here. So if if you consider this is, if you're taking this, if this is the R, yeah, usually we're going to take this to be a Borel sigma field
of the sample space.
Yes. If we take this to be R, I mean the standard scheme, of course. Like I said, unless you want to consider those toys probability space. Toys means there's no actual application, but the purpose is only to demonstrate the what do you call it, for teaching purpose. But usually we won't consider those very funny kind of the 7-6. So when we talk about R or any interval R, okay, the standard option will be the Borel sigma field. Okay.
Okay. I'm getting it, but I'm just. So, but you said that like x squared is not. There's no inverse function for x squared. Then how can you have an? So what if? So RV can't be x squared, no? Basically, not.
No, it's not a function. There's no inverse function from R back to omega. Yeah. You get R and what, but if we consider set, the power set of R and the power set of omega, yeah, we can bring a subset over here back to here. So that is don't forget about the don't go to that. So that is a more abstract kind of the mathematical concept already. Yeah.
Is it then an inverse mapping, or is it?
No, it's not inverse mapping in the usual sense. Okay, because usually when you talk about inverse mapping, you have to require the function to be 1-to-1, then the inverse exit, blah blah blah, and so on. Okay, here this is not an inverse functions in the conventional sense. It's just that something it bring this back to here. Yeah. Okay. So if you want to go in, yeah.
Yeah, sorry, I understand. You can't just throw like a name at me like some weird. It's called blah blah blah. It's not called any particular thing, is it?
I don't want to go into that one. Is even worse. Yes, in fact, if you go into the more advanced kind of the setting, yes, this is a functions. With the, this is a domain and this is a range, but I don't want to go into that. That is getting worse. Okay. I mean, you were lost already. Okay. So just don't get into this kind of. This is, like I said, this is a more advanced kind of the topics in mathematics, so-called the analysis or the advanced calculus. So we are not doing to that level. So at this point, just remember this: a random variable, you have a function. Okay, a random variable is a function from omega to r. All right, sample space to r, and take notes of this. Where is it? So anything inside must be outcome. We are not talking about. Okay. So this is the event. However, what we can do is the inverse or the x inverse. It will bring set back to a set. It will bring an event back to an event, just like that. The inverse image, we call it.
Okay. Yeah.
Okay.
Thank you. No, it's very clear. Thanks.
Yeah. No problem. Oh, okay. So I think more than 5 minutes already. Okay, good. Okay, let's continue to the other sections, right? Wait, where's my questions? So somebody proposed me to discuss these questions 3, 9, and 10. And also just now, I just got somebody leave a message in our group or to personal. So to talk about this question 5. Okay, to ask a question about question 5. So I will just include it into our discussion here. All right. Okay, so maybe let's start. Okay, so let's begin with question 3. Where's my tutorial? Oh, this is a small one. Forget it. So maybe we just look at this. Yeah, so this is the case. Okay. Okay. This is question 3. How come I cannot paste it over here? Got it. Things is that. All right. So question 3. Given subset A and B of omega, so identify all subset in sigma AB. So this is what we so-called sigma field generated by A and B. Okay, so this is a sigma field generated by A and B. Okay, so maybe we get tutorial 1. Okay, first of all, this thing. So this is a so-called the sigma field generated by the class. It's supposed to be a class consists of 2 set A and B. Okay, right. So when this is finite, Okay, so in this case, 2, right? 2 elements. So what we can do is we can do it. What we can do is first we construct a partition. Okay, and then once we construct a partition, and then we list out all the possible union from that partition. Yeah, so this is okay. Okay, so AB, we do not have any information about this AB, whether they have an overlapping part or without any overlapping part. Okay, so let's look at the general. So we put it, so we can have this. So let's say this is our A and this is our B, right? Okay, so this is right. This A, this is B, right? Okay, now we have 4 parts. So which one comes first? So 1, 2, 3, and 4. Okay, we have a 4 part, 1, 2, 3, and 4. So you can see these 4 are disjoint. Okay, so maybe I will put it. So now what we need to do is we just need to so this set 1, set 2, set 3, and set 4 will form a partition for it. You can see it actually cover everything, right? So what we can do is we can set A1 to be, what is this? This is in A, but not in B, right? Or totally, you can say this is an A intersect with a complement of B. And next, we this is the central. I think it's easy. So A and B. Okay. And number 3, so A3 will be in B, but not in A. So likewise, we can write this one as B and AC. And finally, the one at the outside. So this is actually the complement of A union B, right? You can express it in any way, or you can say this is A, C, and B. Okay, or maybe I want to use A. It's a bit confusing. Okay, maybe I will put P1. This is our P2. So this is our P3 and P4. So I think if you look at this picture, you can see P1, P2, P3, P4 are all disjoint. And if you are combining them, you get our omega. Okay, so that's why these 4 form a partition. So this so in here, there is clearly P1, P2, P3, P4 is a partition for our omega. Okay, then what you can do is you can just take it, the union of all of them. So here the cardinality of, so the cardinality is 4, right? So the number of subset will be altogether 16 of them. So that's why in this case, so then you can see the sigma field generated by this, so will be all the possible. Okay, of course, we begin with the empty set. So P1, P2, P3, P4, P1 or P2, and so on. P1, P3, P. Do we have P4? Wow, I think more than that, right? P1 or P4. Wow. P2, P3, P2, P4, P3, P4, and so on. So I don't want to write down. So of course, the last one will be all of them. Okay, so like I said, we have a 4 here, right? So here total will be 16. So here, the total numbers of elements will be 2 power 4, so 16 of them. So you can try to list down all of them. Okay, so that's the way how we construct the sigma field generated by a subclass. So in particular, when our subclass is a finite class, so which means the number of elements here are finite. Okay, so then what we can do is we can construct a partition by using it. So look at here. So when AB, because we don't know whether they have intersections or not, so we assume they do have. So then we have 4. If these two are disjoint, then we have 3. It's simpler. So once we have constructed the partitions, then we list out all the possible union. Okay, all possible union from the partition. So it's not difficult, just like that. Okay. So that is question 3. So next one is question 9. Okay, I have 3 properties to do. So to do this again, we need to make use of the definition for the probability. So what is this? Okay, so definition 1.1.2. So 1, 2, 3 here. So maybe I'll just a revision, just put it over here. Okay, so nice. So just recall the definitions. 1.1.2, there's 2 of them. Okay, first of all, P of omega must be 1, and second, if A is an for event, any event A, so P of A must be non-negative. Okay, of course, number 3 will be the disjoint event. So number 3. Okay, maybe I'm using 1, 2, 3. 1, 2, and 3 here. So supposing we have a disjoint event, we have a sequence of disjoint event. Okay, got to be disjoint. So A1, A2, and so on. So we must have P of union of all the events is equal to we summating P of AK. Okay, so to solve question 9, then we just need to use this 3 properties here. Okay, we go to question A. So A is actually, I believe you should have seen this before. This is the well-known formula in probability theory. PA or B will be PA plus PB minus PA and B. So what we need to do, we just need to use the part 3, the disjoint properties for it. Okay. So again, we just need to split this into different part for it. So supposing this is our A and B. Again, just look at our A and B. So A and B. how should I say it? Okay, so you can look at here. There are 3 disjoint parts for it, right? So this is in A, but not in B. Okay, so this is in B, but not in A. So the middle one will be in A and B. So A or B will be the disjoint of these 3 parts. So if you look at A only, A will be these 2 parts. B will be these 2 parts here. So, okay, so then we can calculate. So from here, then we can see P of A will be equals to, okay, I think maybe I'll do it step by step. Okay, A or B will be these 3. Okay, yeah. So so we can see A or B, there are 3 parts here. A minus B, disjoint union with A and B, and disjoint union with B and A. So if you look at these 2, so it can be written as A, B, disjoint union with B. This is what we can have, right? And okay, we can look at B. So B is a disjoint union of A and B combined with, oh, not this one, don't use this. Okay, maybe you look at A. A is equals to the disjoint unions of A and B. Okay, so we can see this is a disjoint union. So this one also a disjoint union. So once we have a disjoint union, so we can make use of this property 3. So using, so the definition 1.1.2 number 3. So we can have PA or B will be PA but not in B plus PB. So likewise, we can use this. P of A is PA B plus PA and B. So you just take the first equation, subtract the second equations, then you can see PA or B minus PA is equals to PB minus PA and B. So you bring it over, then you will get our equations already. So it's not difficult. You first of all, just to make sure you know how to do this kind of decompositions. Okay, make sure you are able to do a decomposition like this. Okay, so this is a part. Okay, what is a part 2? I think the 3 parts. Okay, B. PA plus PAC is equals to 1. So we can actually make use of this formula here. Okay, so what you can do is, let's say this is A or AC. Okay, maybe we can direct A or AC. Okay, A or AC, and this is A, this is AC, this is A and AC, right? Or maybe we should do another proving first. Maybe we should do this one first. Okay, maybe we do some extra step first. Okay, so this is a extra step. That is a P of empty set is equals to 0. But I think it's obvious. Okay. Okay, what we can do is how I'm supposed to prove this. I think forget it. I also don't know how to do it. Let's assume this is true. Okay, you guys can think about how to prove it. Okay, so for this one, so I want to prove P plus PAC is equals to 1, right? So we are taking B to be A complement. And we can see from part A, okay? Taking B to be the complement of A. So we can have P of A or AC is equals to PA plus PAC minus PA and AC. Yeah. So then I'm going to have P of omega is PA plus PAC minus P empty set. Okay, this is 0, and then this is 1 is equal to P of this one plus this one minus 0. Okay, so this is how we get it. And the next one is straightforward. Okay, so we use back the same formula. Okay, C, I'm going to PA and B greater or equal to PA plus PB minus 1. Okay, we know this PA plus PB minus PA and C is equal to PA or B, and this is always less or equals to 1. So I think from here that is straightforward, right? So then we can see PA plus PB minus 1 is always less or equals to PA and B. Okay, so for question 10, so first of all, given an event A. Okay, first of all, A is an event and P of A is positive. Okay, this is just to ensure our P of A is well defined. So we define PA of B is equals to P of A and, okay, so this is actually the domain, not something in the domain, B here. So you can see all the black color one are fixed already. We have the only variable will be B. Okay, so this is event B. Okay, now we want to prove this PA is a probability on our omega and F. So again, we come back to here. We want to ensure our PA will fulfill these 3 properties. Okay, PA of omega is 1 and so on and so on. Okay, so let's look at the proof here. Okay, so solutions. Okay, one by one. Okay, number 1. what we want to do, just to let you know, we want to show PA omega is equals to 1. So then we just do it. So PA omega, okay, directly substitute P equals to omega. We have P of A omega, or P of A. And A is always subset of omega. So P of A, this is always PA. Hence, we get 1. Okay, so done. This is, we got it, right? Okay, so step 2, what we want to do. Okay, anything here must be positive for anything. I think this is quite obvious. I think it's here. P of A of B is equals to P A and B. So this is always non-negative, right? The reason is for any event B. So this is clear. This is because P is a probability measure. Okay, we can always have this is positive. So I think the second one is quite obvious. So done. So the only challenging part will be part 3. So part 3, what is that? So let's say we consider disjoint events. Okay, B1, B2, and so on. Okay, a sequence of disjoint event. Okay, so what we want to do, so we want to show this PA of union of BK is always equals to be summing up that. Okay, again, I want to highlight, so make sure everything is disjoint here. So we want to show this is equals to this. Okay? So let's proceed. PA of union of all the BK. So I think the first line, according to our definition, this is P of A and all of them. So this is by our definitions. And next, by our De Morgan's law, we can have this. Right? So this is directly by De Morgan's law. Okay, now the question is, we want to know this thing. All this disjoint. See, A and B can disjoint or not? Because of B disjoint, right? So then we can actually show that this one must be disjoint. Huh? Okay. So then we can see since BI and BK are empty set because they are disjoint. So A and BI and A and BK must be also disjoint because this is actually smaller than this. This is smaller than 0, right? So then we got it. Yes, the answer is. So yes, they are disjoint. Okay. Then we can make a conclusion. So hence, those are A of B1, A of intersect with B2, and all these are disjoint event. So most important, we have to ensure this is disjoint. So when this is disjoint, this can be written in form. So then we can see P of A of this. So if this is disjoint, so it can be written as a sum. Summating P of A and BK. Okay, now let's say I change color. So this is, we're just looking at this part only. P, A, and BK. Okay, just look at here. Maybe together with this. Together with this over PA. So if you look at here, then you just look at our tutorial, our question here. Okay, so PA and B, this is actually equals to this one, right? So let's look at here. There's a PK, then this is equals to summating K equals to 1, and which is just equals to PA BK. Okay, so this is equals to this. Okay, so done. So it satisfies these three of them, then we can make conclusions. So BK is a probability measure.
How did you apply De Morgan's law?
Sorry?
How did you apply De Morgan's law? I don't understand how you went from there to there.
Hey, is this so-called De? Oh, sorry, I think this is not De Morgan's law. Sorry, it's not De Morgan's law. What do we call it? Yeah. Sorry, this is not De Morgan's law. Hey, what do we call this again? Distributive. I can't remember. Sorry. Yeah, sorry, it's not De Morgan's law. So this is a distributive law. Okay. Yeah. Okay. So I think we have this result, right? Maybe I just put it over here. Okay. A intercept B union C is equals to A intercept B union A intercept C, right? Okay, maybe I don't want to use C. Instead of C, I'm saying that this is B1, B2. So then I have B1 and B2. I think this is what we so-called distributive law, right? So that's why this thing can be written as union of A and BK. But in this example, we have only 2, right? So that's why it's a K equals to 1, 2, 2. So in fact, even if we're up to B infinity, we will still get the same result. Okay, that's the case for that. So yeah, it's not De Morgan's law because I always use De Morgan's law. So That's okay. So I don't know what you call it, distributive. Okay, you guys go and Google it. So what's the title for this formula? Okay, I think it's distributive law, right? Okay, so last one. Let's go back to questions 5A. Okay, wait, what is it? What is that? To do the answer in the question 1E, question 1, what is it? Why so many questions?
Oh, no, it's just one question. I think maybe there's a typo in question 1E.
I got a typo in question 1E.
Yeah, maybe. Unless I'm wrong.
Oh, okay. Is it just me, or do the answer for problem in question 1E seems wrong? For example, should oh, okay. So thank you, So thank you for answering the question for me. Okay. So I think that's a typo in my solution. So I assume you guys are able to detect it and make a correction accordingly. All right. Thanks a lot, sir. Okay. Okay. Let's get back to our question 5. Well, I got this picture here. Okay, is posted to the, I think it's okay, right? So this is actually in our group. So I think he agreed to share it. So I don't understand what is this. So actually, we are not using this to prove the question 5, right? So let's look at our things. So I can say no.
But is that correct? Is that assumption correct?
This is correct, but we are not using this to prove it, right? We are not using this to prove, but this is correct. Yeah, this is correct. Yeah. Okay, so let's look at our question first. Where's our question? Given two number, show that all these are Borel set. Okay, so this one we have to do it step by step. Okay, so just look at the principles over here. I assume you guys know the construction for the Borel set. Okay, so maybe make it quick. We just briefly look at it. So what is the Borel set? Borel sigma field. How to construct our Borel sigma field? Where is it? Okay, make it quick. Okay, first of all, we consider this kind of open-close interval. Okay, all of this open-close interval. Next, a Borel sigma field is a sigma field which is generated by this kind of interval. Okay, this is one. So which means you take any intersection or union of this kind of thing, so that will be Borel sigma field. Yeah. So now I give you the idea how to do these things. So this is a principle. Just remember this principle. So let's say you said so remember this. Okay. So this principle. You said B is a Borel set. Okay. B is a Borel set provided so either provided okay, I think this is quite simple. B is a Borel set provided B is a union of some non-Borel sets. Okay, nons. I mean, first of all, we cannot start from nothing. we begin with something we know. If B can be expressed as a union of some non-Borel set, it is a Borel set. Or if B is the complement of a non-Borel set, so it is a Borel set. Got it? So this is the principle that we can use. Okay, maybe I need another one. So let's say we put it over here. Forget it. Okay. So this is the one. Okay, maybe I'll put it over here. Let's go something here. Okay. So let's say, according to our constructions, Borel set is generated by open, close interval. So that's why in day one, we know. Day one, we know these kind of things are Borel set. A, B are Borel. Too big. Okay, we know all these kind of interval are Borel set. Day one, we already know. So then we're going to use this kind of interval to produce new Borel set. Okay, so that's why I think this is one all like that. Okay, next we can look at question 5 now. Okay, so let's proceed to question 5. Okay, so what we can do is negative infinity B can always be okay. So the question is, can you write this one in the union of some non-Borel set? Okay, now we know everything like this is a Borel set. Okay, so that's why this one we can put it as union of negative K must be B. So K running from 1 to infinity. So I think it's clear, right? You are just running K from 1 to infinity. So here will blow up to infinity. And clearly, this is an open close interval. So it must be Borel set. So Borel set, right? So this is because we know all these are Borel.
Isn't the plus B redundant?
Not redundant. So for example, let's say this doesn't make any sense, right? So let's say if your B is -5, what is mean by -1, -5? -1 is actually on the right hand side of -5, right? So that's why it's not redundant. So it's either you put K from 1 to infinity, K less than minus K less than B, or blah blah blah. But I think, or we just simply write like this. Okay. Just to make the thing consistent, to be consistent, because otherwise it doesn't make any sense. Okay. So that's the way. So this is or alternately, if you don't want to, okay, maybe I don't want to spoil my picture. How should I say? Okay, maybe you can put it in this way. You can put it in this way. Minus K to B, mathematically, K from 1 to infinity, and minus K less than B. Okay, or you may put it this way. So because of if minus K larger than B, it doesn't make any sense, right? So that's why mathematically, to be consistent, we put it like that. Okay, so this is the first one. Then we can know this is a Borel set. So that's why in day 2, we know this already. We can include this negative infinity to be, so here A, B are real number. So B are real number. Okay, day 1, we know this is Borel set. Day 2, we already know this is a Borel set. Now we're going to use this and this to generate more Borel set. Okay, then wait, why missing? Oh, that's my thing. Okay, where is it? Oh, okay, here. Okay, yeah. So you get an idea? Okay, so now we look at it. So then we can proceed to B. So B, actually, I don't know what is your question. So where is the picture? So I don't understand.
It's not B, it's part 2 of A.
Sorry?
It's part 2 of A. It's not B. It's there's
part
two parts,
right?
question.
Part 2 of A. Yeah, so that's why I'm doing the part yeah. Okay. This is the one. Yeah. Good. So that's why part, we have 2 parts, right? Yeah, so this is part 1. Okay, now we have part 2 of A. Okay, remember, now we have this. We know this and this are Borel set. We're going to use these 2 types to produce more Borel set. So now we want to show this. Negative infinity, B, so now open. Again, can you write this as union of some kind of a non-Borel set? Okay, from 1 to infinity, a countable one, of course, must be. Okay, so I just give you the answer. The answer is, again, we know anything like this will be a Borel set. So this B could be any numbers. Okay, so this can be written as minus infinity B minus 1 over K. Okay, close one. So I think for sure, if you're getting, so this one will, when 1 over infinity will be B, so this will be closer to B minus 0, but never reach B minus 0. Okay, so this is equals to here. So again, so this one is a Borel set. Same argument because of this is Borel set. Okay, so this is how we solve question 5A part 2. Again, we are not using this, right? This one, yes, this doesn't make, we are not using this properties. Yes, this is true. The union of minus K, B open, yes, subset to it, but we are not using this to prove the result. Okay, so we have to construct something. The set will getting larger and larger and close to it. Yeah, so that's the way. Where is it? Okay, here. So then we know this is positive. Okay, so then that means in day 3 we know this already. Negative infinity up to B. So for any B, so this is also a Borel set. And then you can proceed using this. Okay, and in day 4 we know this already. We can just taking the complement. What is the complement for this thing? Oh, so I think in day 4 we know this directly. Day 4. So we can know, we can use this. What is the complement? So A to infinity for any A. This is Borel set, right? Y, I think it's clear, right? So this further is equals to the complement of negative infinity to B, A. So that's why this is another Borel set. So this solve part B, and so on. You guys go and do it one by one. So when you get a more and more Borel set, yeah, then you have more combination that you can get. Okay, that's the way. So we begin with this one, and then with this and this and that. Okay, so I hope you can carry on with the tutorial question here. Okay, the remaining you can do it similarly. Wow, 9:30. Okay, I think I better stop here now. Okay, so I'll see you next Friday. Okay, so have a nice weekend. Any question before that? No more question. Okay, no problem. So